All right. First thing that they want us to do is show that that is the case. Now, often with these, if you can make V the subject, you could just differentiate and show that it satisfies this equation here. If you can differentiate and organise it so that that's the case, you've done it. But every now and then it's easier just to, from scratch, start with this original equation that I'm pointing to and figure out via integration what that circled equation there is. And I think that's what I'm going to do here rather than just differentiate the given one. So I'll just make myself a bit more room here. How about I insert a page break there to get that out of the way. All right. So I'm going to say if dv dt is equal to v10 minus v, then dv on v10 minus v is equal to dt. Now, looking ahead, the thing that I've circled up the top here is like the integral, just not simplified, right? So you can see that it's got two logs in it. Now, when you have a log of v or a log of 10 minus v, you've just got a log of some linear equation, which means the denominators must have been linear. In other words, what we've managed to do is split the 1 on v10 minus v into two linear denominated fractions, partial fractions. And it's what you would have done normally, but the question, the answer there that's circled that you're trying to get to has also indicated that that's what you need, the road you need to go down. So that means that 1 is equal to a10 minus v plus bv, just multiplying left and right by the denominator of v10 minus v. So if I let v equal 0, then I get 1 equals 10a. So a is 1/10, so that's got the first bit done. If I let v equal 10, then I get 1 equal 10b. So b is also equal to a tenth. They're both equal to 1/10, and that's looking good. When you go back up to what I've circled there in the original question, you can see those tenths hanging there. So so far so good. So what I've discovered is that when I go to do this integral of this side, I'm going to re-express it as the integral of 1/10 of on v plus 1/10 on 10 minus v dv equals the integral of dt. So just using partial fractions. So this is 1/10 of the natural log of v and minus 1/10 of the natural log of 10 minus v equaling t plus c. And that's what we've been asked to show, that that's the case there. So that first bit is done. Now, given that v equals v of naught, so when t is naught, we get 5, v of naught equals 5, show that v of t equals all that stuff there. So because t is our variable in our expression for volume, when we put t is 0, we end up with volume equaling 5. So in other words, what they've said here is when t equals 0, v equals 5. That's what they're letting us know. So let's pop those into that equation. A 10th natural log of 5 minus a 10th natural log of 10 minus 5 equals 0 plus c. Well, that's a 10th natural log of 5 minus a 10th natural log of 5. So that's 0, right? So therefore c equals 0. So they've told us that c equals 0, which means we can now go ahead and remember what our aim is. our aim, and now I'm circling the next aim, our aim here is to write the equation with volume V as the subject. That's all we're trying to do. That's what they're getting us to do here, having found C. So we know that we've got a 10th natural log of V, minus a 10th natural log of 10 minus V equals just T, because plus C was 0. And just before I head on, I'm just going to check that that's the original thing I circled up the very top. Yes, that's it. So we've been asked to now make V the subject of that. Sorry, this is I'll undo what I just did. Sorry, I'm just trying to give myself some more room to work, but it's being a bit painful there. All right, so now we're going to put those together using the log laws, like if you've got a log minus a log, because that 10th can come out the front, and we've got a log minus a log. And when you've got a log minus a log, you can put them together as being divided. And then that's natural log of V on 10 minus V equals 10t, just timesing by 10. Raise both sides like e to the power of both sides. So we've got V on 10 minus V equals e to the 10t. So V equals 10 minus V e to the 10t. So V equals 10e to the 10t minus VE to the 10t. So V plus VE to the 10t equals 10e to the 10t. So V into 1 plus e to the 10t equals 10e to the 10t. So V equals 10e to the 10t on, I'll just give myself some room, 1 plus e to the 10t. All right, and I'm just going up to see if this is where we needed to get in their next step. So I'm looking at the question, yep, 10e to the 10t on 1 plus e to the 10t. And the last thing they're saying is obtain the limiting value as t approaches infinity. Now, one little trick here is I would rather have it written with e to the minus x than e to the x, because as x approaches infinity, right, e to the x just goes crazy, right, infinity. But e to the minus x approaches 0. So if I can write things as e to the minus x, they can basically be substituted with 0. So I'm going to divide everything here by e to the 10t. Divide the top and the bottom by e to the 10t. Right? So I've got 10e to the 10t on e to the 10t on 1 on e to the 10t plus e to the 10t on e to the 10t. So as long as you do the top and the bottom of the fraction by the same thing, you're allowed to do that. So that's actually 10 on e to the minus 10t plus 1. Now, when I do the limit, that's going to be a lot easier. The limit as t approaches infinity of v, right, is actually the limit as t approaches infinity of, just need to get a bit of room, of 10 on e to the minus 10 t plus 1, which is just, now this e to the minus 10t becomes 0 because e to the negative something becomes 0. So it approaches 10, and that's the answer they wanted.